Okay, so we left off last time looking at pressure vessels, and we started out with a spherical pressure vessel, and we looked at an element on that, and we found out that the stress in any direction, we'll call it the tangential direction, that would be any tangential direction on that spherical pressure vessel, thin-walled pressure vessel, is equal to the pressure times the radius of the pressure vessel divided by 2 times the thickness. You might say, well, is that inside radius of the pressure vessel or outside radius of the pressure vessel? Well, if it's thin-walled, it really shouldn't matter. It's not going to differ by that much. So the pressure times the radius divided by 2 times the thickness. And what I'd like to do is I'd like to look at an element on the inside of the pressure vessel and an element on the outside of the pressure vessel. So if I look at this, the wall of this pressure vessel here, and I put an element right here where we are going to have some pressure P on the inside. This will be inside. And we're going to say that that pressure is a gauge pressure, so it's above atmospheric. So if I look then at an element on the outside, the pressure here is equal to 0. It's atmospheric pressure. So we'll say that that is 0 gauge pressure. So if I look at those two elements, if I look at the element on the outside, so looking at that element on the outside, I'm going to have something that looks like this, where I'll have these sigma tangential there, and then this radial direction r. I'll just say that that's the radial direction r, and that would be radially from the outside, so we could say something like that. So if I draw a Moore's circle for this thing, I could say that this element, these are sigma tangential, those are both the same value, so I would have a really kind of an interesting circle here right there. There's the xy circle because they're the same value. I could say there's sigma x, there's sigma y, and those are both the tangential value, sigma sub t, the tangential stress. Now, if we come out here and we look, because the pressure here is equal to 0, what's sigma z? It's actually equal to 0, isn't it? Okay, so if I put this, I have then sigma z. We could talk about sigma in the r direction, which would be a sigma z in our case. So we'd have something like that. So we could come up with a Moore's circle that looks something like that. So if we were wanting to find stress values, we would come up to that value there. So that's on the outside. And interestingly enough, it changes if I look at the inside. Well, that's not much of a circle. I need my pencil compass here. But on the inside, so looking at the inside, I have an element that now looks like this. And we'll say in here we now have sigma r is equal to the pressure P. And we have then again this sigma t. And we of course have the sigma t in the other two directions just for equilibrium, but I won't draw those. So if I look at a Moore's circle representation of this one, maybe I better put sigma and tau here. Tau, sigma. Again, the sigma x and sigma y would be the same point. So that's sigma x and sigma y, which are really sigma tangential. And then sigma z, which is going to be equal to sigma r, which is equal to the pressure, isn't it? The pressure would be a value, something like that, that's going to be in compression, hence pressure. So we'd have some value like minus p, and I would then draw the circle looking something like this. So all things being equal, we have larger stress values on the inside, and that's why when you start looking at thicker walled vessels, you usually have failure on the inside. It'll go into the plastic region on the inside sooner. You can get some pretty heavy duty pressure vessels up into hundreds of thousands of psi. A lot of interesting work in this area. Questions with that, whether you're looking on an element on the inside or on the outside? You get the larger stresses on the inside because you have the pressure there. Well, let's move on and do a similar analysis on the cylindrical. So if we look at a cylindrical tank, so on a cylindrical tank here, we said in the longitudinal direction, that would be the long direction, we have the stress being equal to PR over 2T, which would be the same as the cylindrical tank, where we had sigma sub T, the tangential stress. And then it was in the hoop direction, the direction at right angles to that, where this was actually twice that, where this is equal to 2 times the longitudinal stress. Okay, so we saw that we usually had failure in these along something like that. So, well, let's see if I look at an element on the inside and the outside. Again, I could cut a section out of this tank and look at this in the side here. And if I put an element on the inside with some pressure P and an element on the outside with pressure equal to 0, and looking at this radial direction R out from the center of the tank, for something on the outside, I'll do it first again. On the outside, I'm going to have an element that looks something like this, where we've got, let's say, it's not very straight there, sigma hoop, and then we've got sigma longitudinal and sigma sub z, which would be in the r direction, sigma r if you want, or sigma z is equal to 0. So when I put this on the circle, Moore's circle, with sigma and tau, we end up with our hoop stress way out here. There's sigma hoop, and then about half of that is our sigma longitudinal, and we've got a circle right there. Okay, that'd be if I just looked in the longitudinal and the hoop direction, but I have this sigma z equal to 0, so I can plot that point there, and I get an additional circle. I get a couple additional circles. I have this circle like this, which is going to, that's not much of a circle, but you can see you're going to get a much larger shear stress value out of that thing. And you would also in the other direction have that circle. And this is so much more, of course, on the inside. On the inside, we have an element that looks like this, where again we've got the hoop stress and the longitudinal stress, and then I guess back here I didn't do a very good job of drawing that, but back here we would have the pressure, wouldn't we? Which is going to be equal to sigma z, or maybe I should say minus pressure because it's compressive. Well, I've drawn it compressive, so I'll leave it positive. So when I plot this on Moore's circle, again I have the hoop value out there, sigma h, and the longitudinal value, sigma l, and the circle that generates. And now if I look at the z direction, where we have a sigma r or sigma z, that's equal to minus p, isn't it? It's in compression. And that's a little awkward, right? Sigma z is equal to minus p, but I guess this one's because I'm showing in compression. We're probably still okay. So there is a minus p, and we end up with this circle like that. So again, you get your largest stress values on the inside surface of that tank. Questions with that? So you've got some homework problems that deal with pressure vessels and whatnot. Kind of fun to work with. When I was at Precision Cast for a while, we used a pretty interesting pressure vessel. It was about, I think, 4 or 5 feet. It was cylindrical. It was 4 or 5 feet inside, and the walls were about 3 feet thick. So it was a good-sized pressure vessel. And what you did is you put a part in there that had an internal defect. So you'd x-ray it, and it would have some sort of internal defect. And you'd put this part in there, and you'd put oil in there, and you'd heat the whole thing up to about the melting point of the material. And the oil wouldn't catch on fire because you didn't put any oxygen in there. And you would then hopefully, on this part, produce an exterior defect. So you'd smash that in so that that interior defect became an exterior defect, and you could try and weld repair that. So they're running over 100,000 psi in that tank at very high temperatures. So I always thought that was kind of an interesting deal. Well, let's look at some other examples of Moore's circle. It's kind of interesting to see Moore's circle for use in pressure vessels. But if we go back to some of our other examples that we've looked at, we have Moore's circle for axial loads. What's that going to look like? Well, if I draw the stress element here, I have sigma x. That would be just the force divided by the area. And the sigma y would really be equal to 0, wouldn't it? So if I put that on Moore's circle, I end up with a point. There is sigma x, and there is 0. And remember when we went through a problem like this and talked about rotating this element to a certain angle, that was looking at that point there. So those equations that you came up with, you can forget about those. You don't necessarily have to worry about those because you can now deal with this using Moore's circle, which is probably a lot easier than trying to remember those equations. But there is some orientation where you get some maximum shear out of that thing, even though it's strictly an axial loading. Then biaxial stress, a good example might be on a cylindrical pressure vessel, or there's other ways that you can come up with biaxial stress. But let's say in this case that sigma y is equal to sigma x. What's that going to look like on Moore's circle? That's kind of an interesting one. We end up with a circle of radius 0. So there's sigma y and sigma x at that point. And then I think we talked a little bit about pure shear. If I look at pure shear on Moore's circle, pure shear, we'd represent this. If this is the x face and this is the y face, on the x face it tends to rotate it positive, so there would be the x. On the y face it's going to rotate it counterclockwise, so it would be negative. There's y, and we would then, this becomes our diameter, a vertical diameter, and we would draw the circle like that. Okay. And with pure shear, if we rotated that over to here, did we get some maximum value for tension? We did, didn't we? And that's where we saw this crack on here at 45 degrees. You might say, well, there's 90 degrees there, but remember the angle on Moore's circle, we divide that by 2, and we look at the angle on the element. That's why when we were taking that chalk and twisting it, we got that fracture at that classic 45 degrees. So nothing necessarily new here, just talking about what we've done in the past, but representing that with Moore's circle, which again I think is a lot easier than trying to remember the long equations that we came up, particularly for the axial case and for the pure shear case. We can now use our tool Moore's circle to help us with that. Questions of that? Well, let's go to the next subject, which deals with Hooke's law. When we talked about Hooke's law at the very beginning of the term, we looked at a very controlled case. We saw that Hooke's law, that the stress sigma was equal to Young's modulus times the strain epsilon, didn't we? And this was really just uniaxial, one direction. Okay. So we'd like to look at this maybe in multiple directions, biaxial, 2 directions, or maybe all 3 triaxials, look at 3D state of stress. So I'm going to talk about Hooke's law for a 3D state of stress. So we can talk about epsilon x, that would be equal to sigma x over Young's modulus minus Poisson's ratio over Young's modulus times the sum of sigma y plus sigma z. And we could talk then about epsilon y, that would be sigma y over Young's modulus minus Poisson's ratio over Young's modulus times the quantity sigma x plus sigma z. And then epsilon z, that's sigma z over Young's modulus minus Poisson's ratio over Young's modulus times the quantity sigma x plus sigma y. Did we get those all right? I think so. Let me double check that. Yeah, I think we're okay. So this was a very specific case of this. If we wanted to study from the general, we probably should have started with this one, and then we could look at the specific there, but I don't think that would have served us very well. Now, what about shear? We can talk about the shear. If I have gamma xy, that would be tau xy divided by the shear modulus elasticity g, and gamma xz would be tau xz divided by the shear modulus elasticity g, and gamma yz would be equal to tau yz divided by the shear modulus elasticity g. Now if I take these three equations, 1, 2, and 3, and I recombine, so solving 1, 2, and 3 for sigma x, sigma y, and sigma z. So this would be our strain in terms of stress. So strain as a function of stress. If I rearrange these, I could get stress as a function of strain. So let's see what that would look like. We would have sigma x would be equal to Young's modulus divided by 1 plus Poisson's ratio over 1 minus 2 times Poisson's ratio times the quantity 1 minus Poisson's ratio times epsilon x plus Poisson's ratio times epsilon y plus epsilon z. And you can see why we decided not to study this first. Okay. Then sigma y, you can start to see the trend here. We would have Young's modulus divided by, again, 1 plus Poisson's ratio, 1 minus 2 times Poisson's ratio, times the quantity 1 minus Poisson's ratio, times here epsilon y, plus Poisson's ratio times epsilon z plus epsilon x. And the last one you can probably get just by looking at those two. Sigma z is equal to Young's modulus divided by 1 plus Poisson's ratio times 1 minus 2 times Poisson's ratio times 1 minus Poisson's ratio times epsilon z plus Poisson's ratio times epsilon x plus epsilon y. Get those right. Let me double check them. Yeah, I think we're okay. So these equations would be what? Stress as a function or in terms of strain. Okay, so that's the full 3D case. Okay. Now, a lot of times you don't need that. We'll talk about, I mean, this is the general case. If we were to study from the general to the specific, we should have started with this, but I think this is probably easier to, as we began our work. But let's look at some cases that come up. So with this, I'm going to then go to some common variations. Maybe I'll talk about plane stress first. So plane stress What do we mean by plane stress? That would be sigma z is equal to tau xz is equal to tau yz is equal to 0. So all of those are 0. So with plane stress, if I look at the strain equations, I have epsilon x being equal to 1 over Young's modulus times, and that would be, really that's just coming in and taking this requirement here and plugging those zeros into the equations that we had for the full 3D case. And we'd have epsilon x is equal to 1 over Young's modulus times sigma x minus Poisson's ratio times sigma y. And epsilon y is equal to 1 over Young's modulus times sigma y minus Poisson's ratio times sigma x. And epsilon z, there is an epsilon z even though there's not a sigma z. That's really just going to be related by Poisson's ratio minus Poisson's ratio over Young's modulus times sigma x plus sigma y. And we could talk about gamma xy being equal to tau xy over g. We've seen that before. So that's strain in terms of stress. If you want, you could rework these. And I actually did that, sat down and went through that. That's on the website. Let's see, website. Okay, and this, I realize this is too small to look at. It just is something like this. So I went through that. It's got a little bit of algebra in it and whatnot, but I went through it. I'll give you the conclusions here, the starred conclusions. I used to joke about this. If you wanted to freak people out, you just sit at a bus stop going through a calculation like this. But I think they threw someone off of an airplane recently for doing that. So, you know, play that game at your own risk. So we'll go through and rearrange these so that we can come up with stress in terms of strain. So sigma x is equal to Young's modulus, and I'm just giving you the conclusion. There's quite a bit of work here, and that is on the website. So we get E divided by the quantity 1 minus Poisson's ratio squared times epsilon x plus Poisson's ratio times epsilon y. And the other one that we came up with then would be sigma y is equal to Young's modulus E divided by 1 minus Poisson's ratio squared times epsilon y plus Poisson's ratio times epsilon x. Let me double check those. Yeah. So you could take these equations, these up here, and after some rearranging and quite a bit of algebra, which is on the website, you'd come up with those equations. So those are kind of handy. So this is essentially our 2D problem. And then maybe for completeness sake, we'd better look at a 1D problem. We've seen that before, but I think we probably have enough room here. So I'll just tack that right on here. So we'll look at axial stress state. We started with this weeks ago, and let's just say only sigma x is not equal to 0. Everything else is equal to 0. Maybe we could call this our 1D stress state, if you will. So we could say then that epsilon x is equal to sigma x over E. I mean, rearranging that, we have what? Sigma x is equal to Young's modulus times epsilon x. That's what started the whole thing for us. And then what about epsilon y and epsilon z? Well, those are, as we mentioned a long time ago, I think I said that they're not 0, and I don't want to go any further than that. Well, along came Poisson's ratio, and we could define those with Poisson's ratio. So epsilon y is equal to minus Poisson's ratio over E times sigma x. So even though we don't have strain or stress in the y direction, we do have strain, relating it by Poisson's ratio. And we could say that epsilon z is equal to minus Poisson's ratio over Young's modulus times sigma x. Okay. So we have those values that we can use. And you've seen these before, but I just wanted to reiterate those. So that we've looked at the full 3D case, we've looked at the 2D case, and now we've reiterated the 1D case. Well, let's try and put this all to work in an example so it doesn't seem like a pot of alphabet stew or soup exploded on us. So we'll try this example. Okay, so this is a problem that comes up a lot. We take something with a load on it, maybe a piece of machinery or something, we're doing some preliminary design on, some testing on, and we measure the strains. We're not particularly interested in the strains, we'd like the stresses. Stresses are usually fairly hard to measure, strains are usually pretty easy to measure. We can use a strain gauge, and I've talked about this in the past, but a strain gauge might look like this if we have something that has a couple of loads on it. We could put a couple of strain gauges here. We just put this very thin wire and we would bond this. And we could do it a couple different ways like this, so we could get the stresses in one direction and the other. Usually you don't do it just at right angles. You might do it in an equilateral triangle or something. You got some homework problems that'll help you with that. But you can imagine that the gauge in one direction would help relate the stress in one direction, or the strain in one direction to the stress in one direction, and the gauge in the other direction would do likewise. The other thing you'll probably do is have a strain gauge laying over here that takes care of temperature effects, because even if it's not being loaded, as temperature changes, it will probably change its values. Because remember, this was based on the principle that the resistance of the material changed with the resistivity rho times the length divided by the cross-sectional area, right? So as we load this up, if we put a great big load on this in this direction, what happens to the gauge in terms of its length there? It gets longer, doesn't it? Okay? And as we stretch that out, as the length increases, the area decreases and the resistance changes. And it might only be a fraction of an ohm, but gives us a great way to measure this. So we do this a lot in measurement. We are not particularly interested in strain, but we measure strain because it's easy and cheap to measure. Okay, and then we're going to come back and mathematically get from that strain to the stress. So this is a very common calculation for us. Well, we can probably use our plane strain equations, can't we? What if I come back over here and look at these guys? We're looking for sigma x and sigma y. Would that be equation 1 and equation 2? Would that work for us? Should work out okay, shouldn't it? So I could say that sigma x is equal to Young's modulus E divided by 1 minus Poisson's ratio squared times epsilon x plus Poisson's ratio times epsilon y. And then over here we'd have this sigma y being equal to Young's modulus divided by 1 minus Poisson's ratio squared times epsilon y plus Poisson's ratio times epsilon x. So those are our equations. Let's see if they work out for us. So we could say then that sigma x is equal to, E was 200 gigapascals, so I have 200 times 10 to the 9, and that would be what, pascals then, newtons per meter squared, divided by 1 minus 0.3 squared, times then epsilon x, which is 500 times 10 to the minus 6, there's no units there, plus 0.3 times epsilon y, which is 100 times 10 to the minus 6. So you go through the math there, and this turns out to be equal to 116.5 times 10 to the 6, so we'll just call that mega, and it would have the same unit here. This is pascals. So we'd have megapascals. So we can say that sigma x is equal to 116.5 megapascals. When we go through for sigma y, we'd have 200 times 10 to the 9, that's giga, divided by 1 minus 0.3 squared. Then we'll have 100 times 10 to the minus 6 plus 0.3 times 500 times 10 to the minus 6. And in that case, sigma y turns out to be equal to, when you run through the numbers there, 54.9 megapascals. So those would be our answers. And like I say, this is something that comes up all the time. We oftentimes take strain measurements. Strain gauges are cheap, easy to put on, very rugged, they last a long time, they're easy to use, not a particularly expensive measuring equipment that we hook to them. So they've got a lot of advantages. The only problem is we're not interested in the strain, we're interested in the stress. So then we mathematically come up with the stress. So you may have seen them, maybe they've got a suspension on a four-wheel drive or some sort of a race car or something, and they have all these little wires coming off of it to some sort of a data logger in the vehicle, and they're running it around a racetrack. Or maybe they have an airplane wing that's set up in some sort of a jig that they're loading it up, and it has all these little wires coming off of it. That's what they're doing. They've got hundreds or thousands of strain gauges on the thing, and they're monitoring those. Okay. So civil engineers use these, mechanical engineers use these, and so you'll both be going through these calculations. Questions with that? Well, the next place that we will go with this is, let's say, and I think you have a homework problem similar to this. We won't finish this, but I'll just set this up. Let's say that we take a solid steel bore here. So this is very rigid steel, and we put some sort of a rubber plug in there, and then we apply a load to it. And we're interested in the force. You can imagine that that rubber plug is going to try and expand in this and probably put some force on there, and we'd probably like to figure out what that is, right? So we'll go through that. You've got a homework problem similar to that, and that will hopefully allow us to also talk. We're not necessarily going to look at an example like this, but what happens when you have some sort of a press fit? So you take this shaft and you have something that is pressed on it. Is there pressure that's developed here? Yeah, absolutely. And that has to do with the amount of the press fit and the relative stiffness of the two materials. So we'll look at the situations like that and talk about those, and believe it or not, those are going to relate to Hooke's law. And then we'll look at how Hooke's law will transform us into talking about Moore's circle of strain. So that's where we'll go next time. Take care.